Welcome to part B of the first lecture, introductory lecture, titled Architectronics, subtitled Towards Architecture of Mechatronics. Um, we This is not lecture; it's voiceover summary of it. So you might wish to expand it by looking at the slides and reflecting on its delivery a few weeks ago. Um, Let me begin by some reflection about nature of this culture we are dealing with. You're looking at the picture of Cantonese opera house from South China. I think it's from Macau. I've seen it erected within a few days, and it lasts only 5 days to the week during festivals, and used for performances of traditional Chinese opera. Now, this structure is interesting. It is built out of bamboo and it's hand assembled. It's kind of systemic, but it's not really prefabrication per se, though all the pieces are pre-cut. Each piece is different. Each bamboo piece is different. That is case for sort of mass customization, if you like. That's because the bamboos come from a forest and they are given offered to this project by Mother Nature. So not two pieces are identical. Today we are uh, looking at the technologies which have some relation to nature by type of form and generation of geometries. At hand, the complexities are not unlike. Here is a project from MIT scholar Skylar Tibbets. It's installation in a corridor of MIT campus. This is a few years old. It consists of hundreds of vaults. Each vault is different and it's designed with parametric programs fabricated with numerically controlled tools, but it was assembled at hand, so it was kind of time consuming. Here is a process of its assembly um, simulated. As you see, assembly is by hand, not but the production of that and design was done with numerically controlled devices. So that's one aspect of robotics and in architecture. Second part is, I guess, not fabrication, but it's aspects of kinetics present in architectural conditions frequently. Here is a famous imperial villa of Katsura in Kyoto, Japan, and it's all the villa where all the partitions are shoji screens, so they are actually kinetic and mobile, and layout of rooms could be modified depending on the nature of occupants' activity. So this is a very elegant example of architecture which is not fixed, but it is mobile and transformed with use. In our culture, we had I want to use this dressing table, 18th century dressing table, as an example of kind of transformable, um, kinetic, if you like, form. This is a dressing table, ladies' dressing table, which consists of two folding mirrors and drawers, and it's kind of rearranged depending on the need, and then folded together, not uncommon in our cultural tradition, not so frequent in architecture. Let me now come back to the issue of robotics. I want to start with some historical perspective. Of course, there's this famous Leonardo da Vinci sketch of a robotic warrior, and a sketch pretty accurately reconstructed for the museum. You'll see that all the the motion of all the joints is simulated with pulleys and wires. So mechanical part of robotics has been addressed early. Um, Other more contemporary example is work of Nikola Tesla, who used radio waves to control a robot boat or remote controlled boat during the early exhibition end of the 19th century. This is actually um, um, almost 100th anniversary of it. Tesla, who is considered today a father of both radio and robotics, demonstrates his remote control boat, very much underestimated at the time. So you see this tradition is quite old, but quickly it has been brought to military application. We're looking at the Allied soldiers, British soldiers examining Goliath. Those were Nazis' mini tanks. Some of them were radio control and some wired control. And those they carry the super bomb in a sense, or charge, which was detonated at will. They had been used. Those weapons were used during Warsaw Uprising in 1944. So automation and robotics is very much present in today's weaponry as well. We see one of the early American drones, remote control airplane, which carry all kinds of missions. Today, the drones are proliferate in many countries. We see here the catalog of drones, and some of them are huge airplanes, and some of them are miniature. Of course, all this was possible because of early automation, and this goes back to could be placed back to this depiction of the James Watt first steam engine, which was actual automatic system regulating sort of machine with a corrected feedback. So it goes back to 18th century, and this control, this feedback valve was controlling speed of a machine, actually made it all possible. Those contemporary automation, I guess, and robotics own a lot to those early progress in basic engineering and mechanics. Here we look at this wonderful workshop of James Watt, which could be visited still in UK. Robotics are, as a discipline, of course, very young, because even the word itself, robot, was first used by Karl Čapek in his play RUR. This was the early 20s. And he observed in this play that from a time to time we ourselves behave rather like automata, and that we acquired sort of steps or do things repeatedly and turn our lives into stereotypes. And this is kind of brought forward the possibility of having the machines to start taking over the mundane work, which increasingly the machines are more effective, and the movie was proposing that they're also inventive. So this 20s or early modernist kind of celebration of automata was very much prediction of what was to come. Another memorable event from this period is film Metropolis, which I'm sure you've seen, uh, and of course, the robot was then already understood as automechanical device that resembles, in some aspect, resembles humans. But it wasn't until a good 20 years later when MIT Professor Wiener um, formulated the principles of cybernetics as the basics of robotics in scientific terms. Um, it was formulated as interdisciplinary study of the systems, regulatory systems, and related to emerging information theory, control theory, and systems theory. We're connected fields of control systems, electrical network theory, mechanical engineering, logic modeling, even evolutionary biology and neuroscience. Let me offer you a seminal quote from his writing. Wiener says, nervous systems and the automatic machine are fundamentally alike. Nervous system and automatic machine are alike in that they are devices which make decisions on the basis of decisions they made in the past. That's pretty profound observation. Of course, his ideas are related to work of Ludwig von Bartholomä. He is author of general systems theory. It's both of those names you need to know that they are the foundation of mechatronics today. And von Bartholomä was born in Austria, but he was of Hungarian ancestry, and like many early scientists from this modernist period, he ended up in North America. He was somewhat obscure professor and known only to devoted few in Canada for many years. But his writings were discovered at the end of his career, and his general systems theory is now accepted as foundation. He actually was able to put forward the notion of feedback loop, which is, as you well know, essence of any programming today, where the input and output is connected to the feedback loop, and it's sort of illustration of his automation theory as well, and Wiener built on that. So the robotics or robots, autonomous robots that are able to get information about its surroundings and work alone for an extended period of time and operate without human assistance really appeared in practical terms just in the second half of 20th century. So that's a rather new device. Here we're looking at the picture of the first digitally operated and programmable robot. It was named Unimate. The company was two engineers, George Devil and Engelberger, were the authors of this device. And the first installation of this unique first robot was at General Motors, and it was designed to lift hot pieces of metal and stack them in the proper place. But it was programmable and was totally example of the first installation of industrial robot. Today, of course, industrial robots are widespread and deployed in many industrial work much more accurately and reliably than humans. I mean, the best example of it is the car industry, where contemporary cars are far more reliable and durable and efficient in terms of material and design, primarily because of deployment of numerical machines at different stages of the numerically controlled machines at many stages of production. So robots are increasingly used in making, manufacturing, but also in assembly, in packing, in transportation, as we hear, and of course in space exploration, in medicine as well, and unfortunately, as I was indicating before, also in armaments and weaponry, and that is some concern for years to come. Here's another example of the early robot. Unimate also same kind of company from this late 50s, I think, and it was programmable, sort of universal manipulation arm where the basically five freedom of motion was first time put forward, and you see the principles of industrial robots today are still the same, where we have 6 joints allowing considerable degree of freedom in the operation of the arm. So today, I guess robotics could be seen as well established part of engineering and technology, deals with design, construction, operation, manufacture, and application of robots. It is rooted in electronics, engineering, mechanical, classical mechanics too, and software design. So early numerically controlled machines deployed in fabrication have many characteristics of robot or subsets of it. And they are programmable, uh, often dedicated to limited function and purpose, of course, while the fully programmable robot is more universal. It is a growing field as we continue to research and build new robots that serve various purposes, even domestic today. An industrial robot is a very good example, contemporary robot, and this is probably already quite a few years old. Look how big they are. Um, it integrates aspects of electronics, as I said, with mechanical uh, discipline and with computing. So for most mechatronic systems, the main issue is no more how to implement and control the system, but how to implement selected actuators and what is the energy source of the system. Another related and emerging field is biomechatronics, whose purpose is to integrate mechanical parts with a human being, and such examples are exoskeleton, endoprosthetics, illustrated on this slide. But what all this has to do with architecture? I guess a challenge. We challenge you to find out. There is a evidence, growing evidence, that mechatronics is impacting our once very stable and established domain of architectural design. More specifically, the possibilities for architecture exist in 2 areas, and I think this is kind of 2-pronged research going on and among key design schools. First is rather obvious use of industrial robot in fabrication and quick prototyping, um, and actual realization of prototypes. This process already started to redefine the role of architect and changing its role to kind of digital artisan or master craftsman, where not only design but act of production is also very close to his domain. It's almost back to the medieval concept of master builder. Second aspect is use of reconfigurable robotic units or some subsets of this technical culture in designing responsive architecture or its fragments. This type of robotic performative architecture need to understand the environment which it occupies and um, place within that environment and impact on resulting architectonics, which we'll discuss a little bit later. Um, if we look at this diagram, very beautiful diagram, depicting work envelope of the robotic arm, we can think about it in spatial terms. Robots are pieces of mobile architecture. Their relationship to our discipline is manifold and can be regarded from many different perspectives. A robot can be understood as a small model for gigantic mobile building that is able to change its form. Alternatively, it could be part of architectural interior that actively shapes space in the function of uh, integral or dynamic subset of the building or furniture. More conventionally, robots are understood as items for machinery and industrial production, but this is changing. And I would like us to look at those two prongs of support this argument. There's two case studies. The first case study is rather extensive and consists of the work uh, coming out of MIT self-assembly lab, the work of Skylar Tibbets. Uh, he proposed, I think his manifesto is this first sentence: imagine a word constructed of programmable matter and reconfigurable elements. So he envisaged an intelligent environment where objects can take multiple forms and perform range of tasks. This would need to be intertwined with sensing, reasoning, and actuation. The word of self-assembly and reconfigurable units provides exciting vision and a new model for architecture and construction, highly integrated, and where parts have intelligence. They know of each other. Forces are design parameters, and on-demand structure build themselves. Well, that sounds like science fiction, but let's look at the examples. Initially, it would need sensing capabilities and internal logic to construct representation of itself and its environment. This representation should include symbolic description of its parts as vectors and geometric configuration. So that's the kind of paradigm for programming of those devices. It should also include simulations for potential assemblies and analogies of previous events. Consequently, it would also need a specialized critics that can focus on a different task and determine which representation, simulation, or physical output to activate. I think this is a quote from Mervyn Minsky, famous philosopher, also MIT prof. Skylar Tibbets looks at the self-assembly with respect to large-scale structures and chains of assembly. He proposed a framework for creating intelligent systems. He claims that sensing allow for understanding of internal, external state of the assemblies, external sensing for large-scale reconfigurable units, could comprise of sensing temperature, light, humidity, time, movement detection, and many others. Internal sensing, on the other hand, refers to geometric state of the assembly, including engine motor angles, recognizing adjacent units, force detection, and I think location. Internal and external sensing primarily provide data to feed into abstraction of each other and is communicated through the system. Wireless for kind of culture for global communication allows for data to be transferred through the units. As information is shared, it can be processed within each unit to define physical output, which would be passed to activate the assemblies. And the data, of course, could be transferred to internal model. So here is a diagram of vectors he was talking about, and a system symbolic description can be described as a series of those vectors, and each unit or voxel is defined as a single vector and connected to the adjacent neighbors. He is this. I will not go to details with the description. You can read it on the slides later. But basically, the simulation can be generated for potential configuration, and those configurations would be fed by focused goals from environment, spatial, and social kind of feedback. I will move on to a few of his examples. I will go through them very quickly, but you can pursue them slower and read the details. This is a diagram of MacroBot project, which is one of the early projects. All this work is right now a few years old. It will be interesting to see what he's doing most recently. I think I have a glimpse on it. Here is MacroBot chain and diagram. I think one of his first kind of tries was to build letters MIT, which got him a promotion probably. And here the process is repeated through the series of units assembled into chains to create different configuration. And another approach for utilizing MacroBot project as a self-assembly mechanism, growing structures from arbitrary input. This allows the chain robot to become mechanism and discover new geometric structure from varying the input sequences. So here there's exploration in a sense by exploring different consequences of different patterns and spacing of the units. Here we can see the catalog page of possible assemblies exploring the system. And here is finally here's another of his examples. I will not discuss it in detail. It's widely published. And still another one, some of the work of his students exploring different geometric possibilities for those self-assembling units. And the studio at MIT where his students work on this lab. make those prototypes, assemble them into some of the devices we just have seen. And here, a short clip. We attempt to build a space frame, and I think this geometry is quite sophisticated of that, and I think the mechanics are resolved, but I don't think it is actual working model. So some of them are paper tiger, here deployed at the MIT entrance to construction. We look at here another of these devices where actually prototype is working. We see the connectors, kind of bayonet screw connection with embedded electronics and actuators, and the shells ready for assembly. And here we see the display in the form of, I think, almost art installation, which is interactive, but potential of it because of the complexity of joints is considerable. It was a very visible project in the MIT Media Lab about 4 years ago. More recent work concluding this first case study is a project which I think will be seen in the first case study was self-assembly line, which I think is on the verge of toys, but they are very interesting exploration, very original. But second type of case studies here is illustrated with this robotically fabricated thin shell vaulting. It's a fragment of the paper I witness at the presentation I witnessed at the Acadia conference in Alberta a few years ago. It's a very interesting method for integration of multi-axis fabrication process with algorithmic form finding. This fabrication, of course, is possible because of robotic arm. Fabrication process is based on use of abrasive water jet cutter, where ink panels are nested into standard stone slabs, and tectonics design strategy of the vault. Those elements will construct the vault or the arch. No, it's actually vault, hyperbolic, paraboloid surface. Each component of the is self-supporting, part of self-supporting assembly, minimizing the need for form work. The twisting geometry of the self-aligned panel is produced on a 5-axis robotic machine and industrial water jet cutting system. Increased fabrication cost, authors claim, is offset by minimizing formwork and decreasing assembly line, and the potential of the research have been demonstrated through full-scale prototype construction of 2-inch thick sandstone. Um, Here is wedge-shaped blocks, geometry of it, and you can read up on it later, and the project of its process of its production, um, form finding first, and surface description, and finally robotic fabrication indicated here, and then self-supporting assembly. Um, the work of form finding refers to um, an original paper describing parametric software somewhat analogous to work of Gaudi and Freyotto, where inverted models of catenary nets were used in soap films. Uh, Authors concentrated here in the stone fabrication on multi-axis robotic jet cutting, um, using a 7-axis KUKA arm. The control systems have ability to compensate for taper, um, and algorithm was used to control speed and tilting of the nozzle, and in a 5-axis cutting path. So here we see the fragments of these elements assembled. Um, it's perfectly matching and doesn't need any grout. So it's a masonry which is totally seamless, and no loads are transferred between panels and provide full connection. That has kind of brought me to think about this kind of fabrication, which is somewhat analogous to building vaults in Nigeria and Africa, or in self-help unit directed by young architects. They use simple machine to make mud bricks and shells for vault, which required scaffolding. But of course, this kind of technology could be now extended, and once the machines proliferate, I think we can see this vault being built differently. And the vernacular architecture, I guess, to some extent, has this quality of uniqueness. I mean, exemplified by this palm shack from India on beach shack. They are both very beautiful pieces of architecture, and very formally complex. Even they are, by some, you can look at it as primitive. Of course, deployment of robotics in architecture offers this possibility for formal investigations of considerable complexity, as we see today. But one has to remember that early on, as early as 1959, the Professor Zaleski, who was a prof at our faculty, was one of the key designers behind the SuperSum, which has a very beautiful structure, and very organic structure, and very rational structure, where every membrane of this the space beams are unique in many ways. Today it's a breeze with computing, but architecture is entering this field. So let me say a few words about the subtitle of the lecture. Let me talk about mechatronics and architecture. So mechatronics is a multidisciplinary discipline of engineering. There's no reason why it could not embrace architecture, and as a combination of mechanical engineering, electronic engineering, computer engineering, software engineering, and system engineering, all in order to design and fabricate. So mechatronics included just combination of mechanics, electronics, and that's why the word mechatronic was proposed. But current usage of the word has been updated to include more areas, not only technical domains. And thus, I coined this notion of architectronics many years ago, and several years ago, not many, but I show some early work in another lecture. But let me talk about concept alone. And so architectonics could bring about responsive architecture that are architectures that are behavioral, with power to evoke deliberate change in a building fabric. It can provide us with opportunities to tie the formal configuration and qualities of building to social and environmental events. So envelopes and spaces can be programmed to reflect change in season passage of sun, energy consumption, and patterns of usage. This is a freedom of responsive architecture that might be potentially supported by the emerging robotic technology. So this was the ambition of bringing architecture into this diagram together with other disciplines we see here: automotive, aerospace, medical, defense system architecture could be very much part of it. The diagram to support this an early work is depicted here. I think it's 8 years ago. That's quite a bit. But we're designing some installation for seniors, prototyping, and then the diagram I put forward was consisting of analog actuators and digital actuators and sensors and control unit, uh, and we use microprocessors. I think this was maybe Arduino, but I'm not sure. I think we used earlier board than Arduino. Arduino was just starting, and we used a sort of custom board designed by University of British Columbia system engineering students. I think it was never marketed, but proposition here is that giving up land or resources to singular use or intention is not suitable, and it is recognized to be wasteful on many levels, from economical to social. Spaces must function in multiplicity of ways and adapt to multiple uses, adaptable spaces which are responsive to not only to occupants but to environment, can be now produced with mechatronics. On the control system, built form has the ability to adapt, to respond, and to bring a multiplicity to the single design in the previously unknown in architecture. So this was some of the writing, theoretical writing related to those early exercises. This is one of the early VDS Robo studios from 5 years ago in Canada, where we actually was trying to assemble the first working prototypes, and I like this description of the studio, which makes distinction. We owned this lady on a picture who was a mechatronics PhD student, and she explained to students difference between digital and analog inputs when they were positioning those microcontrollers, and I thought was very good, because visually digital looks like this, black and white, on and off, and analog is just shades of gray, and it's a beautiful, simple comparison, and I think richness of analog compared to digital is quite evident in this duality of diagrams. I will finish with an illustration of interactive and adaptive environment coming out of Cornell. Um, this is project for kind of adjustable workspace of furniture, which reconfigures itself to support changing needs, and that might be also worthwhile to look at. In conclusion, I just want to highlight again the schedule to bring to your attention those deadlines where you're supposed to post something on a portal, um, and also highlight the write-up about the aim of Robo Studio, which is an established now tradition in Ask experimental studio, and we we use this particular studio ambition of the studio is exploration of Bluetooth smart devices and in design of robotoys, and those robotoys hopefully are some form of urban subset of urban condition, urban paradigm for the Internet of Things to come. So the robotoys implicitly are part of some larger system, and I want you to stay with this image from New York Times from 1930s, advertising Tinker Toy together with a optional 60 cents, 67 cents price for the electric motor, which would activate the toy. So they were very close already. I think we make one more step.